Hello. Right, so we're going to continue with Coulomb's law today. Excuse me. Okay, so let's go through what we know so far. So we know that the electric force between 2 point charges is given as F equals to Q over 4 pi epsilon r squared. Or sometimes you use Q1, Q2. And then the electric field strength is given as Q over 4 pi epsilon r. And then the electric potential, V, is given as Q over... Oh wait, this one should be... Let me think. E is F over Q CGR squared there. Yep, this one is 4 pi epsilon r. And then the electric potential energy, U, is given as Q times Q2 over 4 pi epsilon r. There we go. So remember the definitions for E is actually force per unit charge, positive charge. Hey Elise, hello, morning. Hello. V is work done per unit positive charge, and electric potential energy is work done. Okay, so that's how I remember it. Okay, so the other thing that I haven't really talked about is what happens to the electric field strength and electric potential when you go, say, inside the surface of a uniformly charged sphere. So let's say we have a sphere, right? Let's say we have a hollow sphere. With some positive charge, positive Q. So this positive charge is distributed evenly on the surface of the sphere. Okay. And then let's say at the center of the sphere, that's when R is 0. And then when you reach the surface of the sphere, this is R equals to capital R. And then you can keep going. Okay. So if you were to draw a graph, excuse me, if you were to draw a graph of electric potential against the distance r from the center, if you are referring to a point charge, so all the charge is concentrated at the center. Okay, so this one is hollow sphere, this one is point charge. So these equations that we have got on the left only apply to point charges. Okay, so for a hollow sphere, if you are looking at a point that is not inside the surface of the sphere, you can kind of assume that this is a point charge, especially if you are very far away from the sphere itself, then you can assume it's the same as a point charge. It is indistinguishable from a point charge. However, if you go, if you're trying to put a test charge inside the surface of the sphere, then it will not behave as a point charge anymore because the charge is actually distributed uniformly across the surface, right? So imagine you have, this is the hollow surface, and then you have a test charge here. So this guy is a positive test charge. Right? The test charge by convention is always positive. So if you put a positive test charge in here, it's going to and let's say the charge on the surface is also positive, it's going to experience some force of some repulsive force due to the positive charges on the surface. And because this point charge is closer to this surface over here, then it would experience a greater force. But then there are more charges over here, right? So the charges over here would also push on this point, this positive test charge. But because the distance is further away, it pushes with less magnitude. But there are actually more charges here compared to this one. So in fact, if you work out the integral, you would actually see that the resultant force experienced by the positive test charge when it's inside the surface of the sphere is actually 0. Okay, so resultant force in all directions is going to be 0. So you don't have to know how to do the integral if you're doing like maybe engineering or physics, then you learn how to do that in university. But this is not in the in your syllabus. You don't have to know exactly how you go about calculating this. But suffice to say, resultant force is 0. Okay, so what does that mean for the electric potential then? How would you draw the electric potential graph? Okay, so before we do that, let's try to draw the electric field strength graph. So the electric field strength graph. So remember, electric field strength is force per unit charge. So electric field strength is proportional to force. The Q here, this big Q here, refers to the charge of the holosphere, not the charge of the test charge. Okay, so this Q is actually some constant value, which means your E is proportional to F. So if you want to plot E, you're essentially plotting F. The shape of the graph will be similar to that of F. So if you look at F here, the only variables are R, right? So that means F is, so E is inversely proportional to R squared. So you're essentially plotting something like a 1 over x squared graph. So you would expect to get something like this. Okay, that's what a 1 over x squared graph looks like. You have an asymptote on the x equals 0 axis and y equals 0 axis. But this is if it's a point charge, right? However, for a holosphere, it is not a point charge. So what do you do? Well, for a holosphere, we know that when you go under the surface of the sphere, the resultant force is 0. If your resultant force is 0, that means the force experienced by the positive test charge will also be 0, which means your electric field strength would also be 0. Okay, so let's say we're gonna call this point here R equals to R. So from this point onwards, it should be 0. So we shouldn't draw it like that. In fact, it's gonna look something like this, and then 0. There. So it just falls to 0. Okay, so that's how you're supposed to draw it. Now, what about a electric potential against R? How would you draw this then? So remember what I told you last class? In physics, the convention is any positive charge or mass would tend towards a region of lower potential, right? And V is actually going to be oh wait, I've already written it there. V is Q over 4 pi epsilon R, right? So we know V must be inversely proportional to 1 over R because R is the only variable here. So you are essentially kind of drawing a 1 over x graph, which kind of looks like this. Very similar to x squared, 1 over x squared. Okay, so suppose this is the point where R is equals to the radius of the hollow surface, hollow sphere, right? What is this going to look like then? Well, is it going to look like this? The answer is not really, because if it looks like this and you have a charge at the surface, it's going to feel an attraction towards the center of the sphere, right? Which doesn't really make any sense if you think about it, because your test charge is positive and your sphere is positive. So there shouldn't be some kind of attraction towards the center of the sphere. It just doesn't add up, right? So we know that this line cannot be lower than the highest point over here. So, and we also know that the potential gradient is proportional to the magnitude of the electric field strength. No, actually, not. Try it like that. E is equals to negative dV dr. No, it should be proportional. So the electric field strength is proportional to the potential gradient. So the gradient on this graph down here, the negative of that gradient, would actually give you the electric field strength. Okay, so if my electric field strength is 0, as we have shown over here, that means you expect the gradient to also be 0. So what does a curve with gradient 0 look like? It's just a horizontal line, yes? So we know that it looks like a horizontal line, and we also know that this horizontal line cannot be lower than this highest point here. Well, this point here. So we have to draw the line like this. So that's how the potential R graph looks like. So if you think about it, let's say I put a positive test charge somewhere here. It's going to be attracted to a region of lower electric potential. So it's going to go this way, which makes sense because positive charges, like charges repel. And if you put the positive charge on the surface or anywhere inside the sphere, it's not going to experience any force as well because the gradient is 0, which is what you expect to get. So that's the reason behind how you're drawing it like this. Okay, so let's just compare this with the gravitational field strength. Okay, so for gravitational field strength, hang on, let me just write that here. E is proportional to negative dV dr. Okay, let me get rid of this. So for a massive object or an object with mass, if I were to plot the gravitational field strength against R, and let's say we have a planet, at the center R is 0, at the surface R is equals to R, and then this extends all the way there. So this is some planet with mass m. Okay, so we know that G is equals to gm over R squared. G and m are constants, so G is inversely proportional to R squared. So you're essentially plotting 1 over x squared, similar to what we're doing on the electric field strength here. So if you were to draw it, it kind of looks like that. Okay, and remember that for gravitational field strength, let's say this is R equals R, this thing actually decreases linearly. It goes like that. So one of the main differences between these two models is that this is not a hollow planet. This one is actually a, it's filled with mass, a uniform density planet, right? So that's different to this one. If you have a hollow planet, then you would actually get something like that instead. Okay, so instead of this, you would get a straight line down. And then for gravitational potential, hang on, gravitational potential is a bit different. Hang on, get the thing here. Gravitational potential, V against R. So gravitational potential is negative gm of R. So you're plotting y proportional to negative 1 of x, which means it kind of looks like this. Right, and then if this is R equals to R, what happens here? I think from here it's actually a cubic graph. So from here to here is like a, if I'm not mistaken, it's like a some kind of negative cubic or something. I can't quite remember. But the shape is very similar to 1 over x, so it still looks something like this. Okay. So if you think about it, for a massive object, when you put the test mass inside the object, it's still going to be attracted towards the center, right? So the gravitational potential should decrease all the way to the center. So the center should have the lowest gravitational potential. So you always expect this part here to decrease. That's why it kind of looks like this in the first place. Right, so there we go. That's the difference between the two. Very similar, but not quite the same. Okay, all good? And then let's just compare this with, actually no. Nah, I think you don't have to do that. Okay, this is fine. All right, all good. Moving on. Okay, this one we'll talk about that later. So we'll talk about this later. Let's do this one first. Okay, so you have an isolated conducting sphere of some radius r with some positive charge. This charge may be assumed to act as a point charge situated at the center, blah blah blah. The figure below shows the variation with distance x from the center of the sphere due to the charge. Okay, as you can see, this is the potential x graph, and you can see that the line is like that, like what we drew earlier. State the relation between the electric field and potential. So how does the electric field relate to the potential? Well, actually, that's a electric field strength. So I've actually kind of told you the answer to this already. Right? It's E is proportional to negative dVdr. So you could say that electric field strength is proportional to the negative of the potential gradient. So this guy here is called the potential gradient. There we go. Using the relation in A, sketch a graph to show the variation of distance x of the electric field E due to the charge Q. So this is electric field strength. Okay, so you kind of know what to do, right? Kind of looks like this, and then you go like that, and then this should be a group down there like this. Oh, by the way, I should mention that you shouldn't draw a line between this and this. So let me just go back here. You shouldn't draw this line over here. Don't draw this line. There. Okay. Next up, in a particular experiment, a high voltage is created by charging an isolated metal sphere. So you charge this metal sphere. This sphere has some diameter 42 centimeters. Any charge may be considered if it's concentrated at the center. The air surrounding the sphere loses the insulating properties, causing a spark when the electric field exceeds 20 kilovolts per centimeters. By reference to an atom in the air suggests the mechanism by which the electric field causes the air to become conducting. Okay, so how does the electric field cause air to become conducting? So I'm not sure whether you have seen this before, but there are things called Tesla coils. They kind of look like, something like this. You have these coils around, and then you have another thing. They're called Tesla coils. And if you connect these two and then you increase the potential difference between them to some value, if you keep increasing it, eventually the electric field will be so strong that electricity would start to arc across the air, and then you can see sort of like this arcs of lightning going bazap, bazip, bazap. So that's a Tesla coil. So The question is saying that once you increase the electric field to some value, you get a spark in the air. So spark essentially means current traveling through the air. So how does that happen? Well, molecules in the air have electrons and protons, right? Or any kind of atom in the air have electrons and protons. So if you have an electric field, so let's say this is positively charged. So let's say you have some electric field, and as you increase this electric field, the particles in the air, the molecules, or whatever, let's say this is the proton of the particle, and this is the cloud of electrons. And then you have your electric field going like this. So this electric field would cause the electrons to experience a force in this direction, but the protons will experience a force in this direction, right? But because of the bond between the protons and the electrons, they're sort of held together. But if you increase the electric field so that it's strong enough to pull apart the electrons and the protons, and the electrons move freely, then you get a current, and then you get a spark. Zap, zap. Okay, so that is the mechanism behind this. So that's what you want to say. So you say the field causes forces on the electrons and the nucleus to be in opposite directions, and it causes the electrons to be stripped off the atom, and then you get a spark. There. Okay. Okay, moving on. Calculate for the charge sphere when a spark is about to occur, the charge on the sphere. So, well, we know that the spark happens when electric field is 20. So let's write that down. Electric field is 20 kilovolts. What is the formula for electric field? Electric field strength is going to be force per unit charge. So Q1, Q2 over 4 pi epsilon r squared. There's only one Q, sorry. There we go. Okay. So Q is going to be this guy here. What is R going to be? R is actually the radius to radius of the sphere. So why do I use the radius? Because it says here the charge on the sphere. Yeah, so the spark happens on the sphere, which means the spark is a distance radius away from the sphere. That's why we're using R. So R is actually 21 centimeters. So this is going to be 4 pi epsilon is 8.85 times 10 power minus 12. Oh, not 15. Okay. And then you work it out, and voila la, you get your answer, which is 9.8 times 10 to the power negative 6. There you go. Okay. Next up, you're asked to find the potential. So potential is going to be Q over 4 pi epsilon r. Or you could say it's E times R. So E is going to be what we got earlier. 9.8 times 10 to the power 6, negative 6. Oh, wait, no. This one is actually our charge. What am I saying? Q is actually our charge. Never mind. 9.8 times 10 to the power minus 6. And then you put in your values. And you get your answer. Okay, that's about it really. Which is 4.2 times 10 to the power 5. And next up, use under certain conditions, a spark sometimes occurs before the potential reaches that calculated in this. Suggest a reason for this. So this is an ideal condition, right? We're assuming that the sphere is perfectly spherical. There are no imperfections on the surface of the sphere. We're assuming there's no humidity in the air, because humidity would introduce water. Water is a polar molecule. Well, you've done chemistry, so you should know that, which means they are more easily, you can pull them apart much easier, which means you would need a lower value than this to cause a spark. Basically, you just quote reasons that may suggest it is not ideal. So things like the sphere is not smooth, there are imperfections on the sphere, the air is humid, and yep, that's pretty much it. Okay. Question 3. The definitions of electric potential and of gravitational potential have some similarity. State one similarity between these two definitions. So, name one similarity between gravitational potential and electric potential? So I'll tell you that the similarity is they are both defined to be 0 at infinity. There. Explain why values of gravitational potential are always negative, whereas values of electric potential may be positive or negative. So this has to do with the nature of gravity and charges. Charges can be positive or negative, so they can be attractive or repulsive, but gravitational force is always attractive. So that's what you want to say. Okay, essentially that's what you say here. Gravitational forces are always attractive. Electric forces can be attractive or repulsive. And then you also want to say, for gravity, work got out as masses come together. So this one is, okay, how should I explain this? So work got out is actually another way of saying work done by mass. Okay, so if you put a mass in the vicinity or in the gravitational field of another mass, you don't have to put in any additional work on your part to push this mass towards the other mass, because when you release this mass, it's going to slowly move itself towards the other mass because there is some force of attraction, right? So you don't have to do any work. So no work is done on the mass. So work is done by the mass because the mass itself moves without needing any external force. So that's what it means by work got out. It's the same as work done by the mass. Okay, so that's what the sentence means. And then for this one, for electric charges, work done on charges if same sign, work done by charges if opposite sign, as charges come together. So if you have two charges and they are like charges, and you want to put them together, you have to put in additional work, because if you leave them as they are going to push themselves apart because like charges repel. So if you want to push them together, you have to put in work. That's what this is saying. Work done on charges as charges come together. So you have to do the work. But if they are opposite signs, work is done by the charge, or work got out. Okay, so you have to code these 4 things whenever they ask you for why the potential is negative for this, but it could be not negative for this. This is what you say. Okay, pretty standard answer. Oh, oops, wrong one. All right, next up, state Coulomb's law. So Coulomb's law is, well, you're just saying that the electric force between 2 point charges is proportional to the product of the charges and inversely proportional to the square of the distance between them. You also have to mention point charges. Okay, obviously don't write it out like that. Write it out in full using words, right? So you say electric force between 2 point charges proportional to the product of the charges, inversely proportional to the square of the distance between them. But this one was actually, we've done the definition before, so I'm not going to write it out again. Okay, so moving on to part B. 2 charged metal spheres A and B are in a vacuum as shown. The shortest distance between the surface of the sphere is 6 centimeters. A movable point P lies along the sign joining the centers. Okay. The variation with distance x of the electric field strength at point P is shown below. So what exactly is this graph? What is this graph telling us? So let me just zoom out a bit more so you can actually see the diagram here. So this P here, and if you read this sentence here, it says the variation with distance x of the electric field strength E at point P. So this is actually the resultant electric field strength. Okay, it's not the electric field strength due to A or B. It is the resultant electric field strength due to both spheres. So the question is, how do I find the resultant electric field strength? Because the electric field strength is actually given as Q over 4 pi epsilon r squared, right? But this is only for 1 point charge, not 2 charges. So if you want to find the resultant electric field strength, you actually have to take the electric field strength due to A plus the electric field strength due to B. Kind of like when you're doing the resultant force equation or resultant moment equation, right? Your resultant means added up. However, you have to be careful because if you're adding up scalar quantities, you can just add them up. But if you're adding up vector quantities, you have to put in the correct sign as well. Kind of like when you're doing resultant force. If one force is this way, one force is that way, then you have to take this force minus this force, right? Or in other words, you can think of it as this force plus the negative of this force. So it's kind of the same thing here. Now, both of these spheres, both of these spheres, we don't know what the charges are. It could be positive, positive, negative, negative, or maybe they are oppositely charged. We don't know, right? So let me just scroll up here. So if you look at page 6 of your notes, you have 2 spheres, right? And let's say the electric field strength of sphere A, we can write it as this guy right here. You can see it, right? So the charge of A over 4 pi epsilon r squared. So r is going to be the radius of A, so from here to here, plus x, because this is the distance from the center to point P. because we are treating the sphere A as a point charge. So that we're assuming that the charge they're concentrated at the center of these spheres. Okay, because when we use these equations, we have to assume they are point charges. Okay, right. What else? So for the electric field string at sphere B, you would be taking the radius of sphere B plus this distance here, which is y minus x. So you get this. Okay. And the resultant force is going to be the electric field strength of A plus the negative of the electric field strength from B, because the electric field strengths are oppositely directed. It doesn't have anything to do with the charges actually at this point. So how should I explain this? You see this R here? Actually, no. How do I explain this? What's the best way to explain this? Okay, so from sphere A's perspective, going to the right is positive. From sphere B's perspective, going to the left is positive. Well, no. No. I don't think that makes any sense. Okay, so the electric fields are being projected in opposite directions. So one is going to the right, one is going to the left. So basically, because they're vectors, they should be oppositely directed. If I can think of a better explanation than that, then I'll come back to this. Hey, Modus, your favorite chapter. So whenever you add electric field strength, you must always put a negative on the other one. So it kind of looks like this. This one minus this one. Okay? So this one is just some extra fluff, not important. Okay, so if you have two spheres that are positively charged, you would actually get a graph that looks like this. And the way you make sense of this graph, okay, so going to the right is positive, going to the left is negative, okay? The convention could be the other way around. But, I mean, it depends whether the question tells you whether the convention is this way or that way. But the point is, one way will be positive, one way will be negative, okay? So for this specific scenario, I'm going to go with this convention. So you can see here, if I take my test charge, let's say I have two spheres, sphere A and sphere B, and then I have a test charge which I'll call P. If I put P at this point here, if I put P exactly in the middle, my resultant electric field strength is 0. What does that mean? That means it's not going to experience any force. The resultant force will be 0. And if you think about it, it kind of makes sense because assuming these spheres have the same charge and you put another test charge in the middle, remember a test charge is always positive. If you put a test charge in the middle, this test charge is going to experience two forces in opposite directions from A and B. And if they're the same magnitude, then the resultant force will be zero as well. So far, so good. But if you put the test charge closer to B over here, you see that my resultant electric field strength is negative. What does negative mean? Negative means it goes in the opposite direction, it goes to the left. So if I put a positive charge over here, because it is much closer to B, and remember that the electric force is equals to Q1, Q2 over 4 pi epsilon not R squared. So Q1 would refer to the charge of P, Q2 would refer to the charge of B, right? So this is the force between P and B. So you can see that the force is inversely proportional to R squared. So the closer you are to B, the stronger the force is going to get. So if you put P very close to B, the force is going to be much bigger to the left and a bit smaller from the right because it is further from A. So you're going to get a resultant force towards the left, which means your electric field strength would be negative because it's going to the left. That's why you get negative over here when it's closer to B. Does that make sense? And if you move it closer to A, you see that the resultant electric field strength becomes positive because now A is going to push back stronger than B, so it's going to push it to the right. There you go. Okay, so what happens if we have A is positively charged, but B is negatively charged? So we have A is positively charged, B is negatively charged, and you put a test charge in the middle. Remember, the test charge is always positive. So what happens to this test charge? Well, it's going to experience a push force from A and a pull force from B. So you should expect P to move in the positive direction because positive is, going to the right. So if you look at this graph here, you see that it is always positive. Oh. So no matter where you are between A and B, you will always be pushed to the right, which makes sense, right? Okay. Let me show you what this looks like on Desmos. So if you add up these two electric field strengths, you will get this thing here. If I simplify it a bit, I will eventually, and I make some assumptions, I'm going to say the charge is 1. So you can get rid of this 1, this QA and QB. Because if I want to plot something in Desmos, I need to make some assumptions. Otherwise, I have too many unknowns. The distance between the surface of the sphere, we're going to say is 4. Okay, so we're going to say y is 4. And then the radii of both spheres, we're going to say is 1 respectively. So we're also going to say that the proportionality constant is 1, just to make things simpler a bit. So if you have two spheres that are positively charged, this one and this one, and if I plot it on Desmos, okay, so the first one is going to be y equals to 1 over x plus 1 squared. Okay, so the next one is going to be y equals to negative 1. Well, technically it's 1 over 5 minus x squared. There. So remember the cross-section of the potential well, right? The 2D potential well that I showed you last class. If you have a positive charge, it kind of looks like this. And the center here is where the positive charge is. Okay? But when you want to add these things up, you have to take the red one and you subtract that with the blue one. Okay, so take this, add it with this, and you would actually get this guy here. So if I take all of that, can I paste it here? Yeah. And I cut that away. Wait a minute. Why does it look different? Oh, no, that's correct. Yeah. So it's from here to here. So if you have a zoom in, go away. If I zoom in, you see this part to this part. That's actually this part here. See, that's what it looks like. This is where the center is. But we know that this is a hollow sphere. So in fact, it shouldn't actually look like this. In fact, when it comes here, it should drop down to 0. And when it goes here, it should drop down to 0 as well. Because, like I said earlier, for a hollow sphere, when you go inside the sphere, electric field strength drops to 0. Okay, so that's what it looks like. And that's how I get these graphs in the first place. Okay, continue. What if we have two negatively charged spheres? Well, if you have two negatively charged spheres, let's say I have sphere A negatively charged, sphere B negatively charged. I put the test charge here. It's going to experience a force in both directions, which means if I put it smack in the middle, I should have 0 resultant electric field strength. If I put it towards A, it's going to move towards A, which means you should have a negative electric field strength. If I put it closer to B, it's going to move towards B, so it's going to have a positive electric field strength because it's moving to the right. So that's why you get this graph here. Okay? So that's how you sort of make sense of this graph. You need to know how to make sense of these graphs because the question that we were doing earlier kind of looks like this. As you say, use the figure above to explain whether the two spheres have charges of same or opposite signs. What do you think? Same or opposite? Well, in this case, we are not given the convention. The question doesn't tell you going to the right is positive or going to the left is positive. So who knows, right? But they're not asking you whether it's positive, positive, or negative, negative. They're asking you whether they're the same or opposite. So if you have two positive charges, and you put a positive test charge in the middle, you can see that this is 0. So that is one of the characteristic thing that you should look out for. If you can see that at some point in the middle, it doesn't have to be the middle because maybe sphere A has more charge than B, so it could be slightly towards A, or it could be slightly towards B. But the point is, if you see that at some point you have electric field strength as 0, that means it has to be same. The charges have to be the same, because this would not happen if you have opposite charges. Okay? So, what you are supposed to write is this. Fields are in opposite directions. And then you say the point where the fields are equal and opposite, the field strength is 0. Therefore, it is the same charge. If going to the right is positive, going to the left is negative, then we know that both charges must be positive. If the convention is different, then both charges are negative. But they're not asking you that. They're asking you whether they are the same or not. And they are the same because there's a point where the field strength is 0. Okay, so that's what you want to say. Yep, all good? All right, let's go back and cover the rest of these questions. Where is it? There. So we have one more scenario. If you have two spheres and they're all, and sphere A is negatively charged, but sphere B is positively charged, what happens? If we put a positive test charge here, it's going to experience a force to the left, like so. So at any point in time, it's always going to experience a force to the left, which means your resultant electric field strength must be negative at all times. And as you can see from the graph here, it is always negative. Therefore, there it is. Yeah. Okay. Alrighty. What about electric potential? Wait, is there a question involving electric potential? Let me just check. No, I don't have a question involving electric potential, so I think we have to do an electric potential question from the past year because that one is also quite important to talk about. Okay, so let's do this one here. You have a proton at a point P. Use data from the graph to determine the acceleration of the proton. All right, so this is where x is 5. So 5 is here. So resultant electric field strength is -3 times 10 to the power of 3. Okay. So resultant electric field strength is -3 times 10 to the power of 3. So how do I find the acceleration of the proton? So what is electric field strength? Electric field strength is force per unit charge, right? And force is actually ma, assuming your mass is constant, which it is in this case. So A is going to be Q times resultant electric field strength divided by m, the mass of the proton. So Q is the charge of a proton, which is positive 1.6 times 10 to the negative 19. Electric field strength is, -3 times 10 to the power 3. And then your mass of a proton is 1.67 times 10 to the power of negative 27. So you put that into this, and then you get your acceleration done, which is going to be 2.9 times 10 to the power of 11. Okay, and then going back here. Use data from the graph to state the value of x at which the rate of change of electric potential is maximum. Give the reason for the value you have chosen. All right. Rate of change of electric potential is a maximum. So, rate of change of electric potential. So this is actually dVdr, right? So they want dVdr as a maximum. So what is dVdr and how is it related to E? So we know that dVdr is equals to negative E. So we're looking for E, where E is some maximum negative value. So the maximum negative value is probably this guy here, right? Which is -14, I guess. So this is the maximum value of the rate of change of electric potential. So where does that happen? That happens around x is equals to 6. And done. There you go. So you have to quote the equation where the field strength is the potential gradient. And then you have to write this down. There you go. Whew. Okay. All right, we still have 1/3 of the chapter left. We're gonna finish the rest of this on Friday. Yeah, and then we will be done with this chapter. And yeah, so Friday will be our very last class. Okay. I shall see you guys later for maths. We will be doing numerical solutions of equations. Bye bye.